right, so dilation, stretching and compressing. If we multiply a function by a non-zero real number, it has the effect of either stretching or compressing the function, because it causes the function value, the y, to be multiplied by that number. So if we think of vertically stretching, our graph gets skinnier, right? If we're vertically compressing, our graph is going to get fatter because it's going to grow slower. Let's try some functions multiplied by non-zero real numbers to see what this looks like. And this part's not in your notes. So we'll look at parabolas and we're going to look at absolute value. So when a number k is multiplied with the x in f of x, the graph will stretch or shrink horizontally. This is called a dilation. Now you can think of it as stretching or shrinking horizontally or stretching or shrinking vertically, right? So if you stretch horizontally, you're shrinking vertically. If you shrink horizontally, you're stretching vertically. Right? Same thing. All right, so here on the left we have the graph of y equals x squared. Again, got this crazy scale going on the y-axis. But maybe it's so that you can have the same crazy scale on both of those graphs, because the second one is growing pretty fast. So we have y equals x squared. A pretty clear point is the point 525, right? And even if we weren't sure, if we plug 5 in, 5 squared is definitely 25. Let's look at the graph on the right, right? So that's 2x all in parentheses squared. So that means both the 2 and the x are squared. When you have a product, you do distribute the exponent to the product. You never distribute it to a sum or difference. It doesn't work that way. We would multiply the sum or difference by itself. But if you have a product, so 2x squared and 2 squared times x squared is the exact same thing. So 2x all squared is 4x squared. Let's look at what happens to the y value for that very same x value. So now if we look at 5 on our graph, it is no longer at 25, it's at 100. So notice that if we have a coefficient in front of x, the y value is going to be that many times greater than it was. So in other words, if we have 25 as the y value for x squared, for y equals 4x squared, that 25 is going to be 4 times as much, right? So, or 100. We can use that fact to stretch and compress our graph. But right now, we're just going to focus on noticing what's happening. We'll worry about graphing in the next video. So when a is negative and multiplied by f of x, the function will flip over the x-axis. This is called a reflection. Right? So what's going to happen if we have a negative a value, I'll put it down here, I guess. So if we have a negative a, the y values become the opposite, because we're going to be multiplying by a negative number. All right, so here on the left we have 2x squared. On the right we have negative 2x squared. So right here we can see a pretty clear point. Right? This is the point 550. If we were to square 5, we would have 25. 2 times 5 is 50. So that is the point 550. If we look at the graph on the right-hand side, y equals negative 2x squared, we have that same point at 5, but instead of being at positive 50, it's going to be at negative 50. Right? And that's because that negative a value has reflected our graph across the x-axis. Right, so now let's look at the same thing, but now we're going to look at it with absolute value. Right, so we have 2 times f of x. Right, so we have 2 times the absolute value of x and 4 times f of x, 4 times the absolute value of x. And then of course our parent graph was just f of x equals the absolute value of x. Right, so now notice that the graph isn't moving at all, it's just becoming skinnier. And that's because we have an a value that is greater than 1. Right? So in all of these, the vertex here is at 0, 0. Let's look at a comparable point. So on the blue graph, we have the point 1, 1. Okay. If we look at the y value, when x is 1 for the red graph, we have the point 1, 2. Notice it's twice as much, and that's because we have 2 times the absolute value of x. If we look at a similar point on the green graph, right, so if we go to where x is 1 on the green graph, the y value now is going to be 4. So notice that for the same x value, our y value is going to be whatever the a value is times the y value for the parent graph. Right? In this case, 2 times 1 and 4 times 1. So notice for any x on the graph, the new green graph has a y value that is 4 times as much as the original blue graph. If we're looking at y equals 2 times the absolute value of x, now our graph has a y value that is 2 times the y value of the parent function. Which is the blue graph. So the graph AF times f of x, where a is any real number greater than 1, is the graph of f of x, but vertically stretched or dilated by a factor of a. So we're keeping the x values, the y values just become whatever the y value was times a. Okay, times that amount that we're stretching our graph by. All right, so now let's look at these ones. So now the value of a is positive, but it's less than 1. It's between 0 and 1. All right, so again, the vertex for all these graphs is 0, 0. We're not translating. Right? We're just dilating here. All right, let's look at the green graph and the red graph. I guess we'll look at our comparable points first. All right, so probably the easiest one to see is what if we used 4, right? So 4 on the x. All right, so here on the blue graph, when x is 4, y is also 4. How about on the red graph? Well, when x is 4, y is only 2. And how about on the green graph? When x is 4, y is only 1. So now the same thing is happening. Right? So the y value is just the y value for the original parent graph multiplied by whatever a is. So if we take 4 times a half, we would get 2. If we take 4 times a fourth, we would get 1. So notice for any x on the graph, the new green graph has a y value that is 1/4 as much as the original blue graph's y value. And if we're looking at the red graph, 1/2 of times f of x, or 1/2 times the absolute value of x, the y value is 1/2. The y value of the parent function, which of course is y equals, or f of x equals, the absolute value of x. Right? So the graph a times f of x, where a is between 0 and 1, is the graph of f of x, but vertically compressed or dilated by a factor of a. So notice now our graph is growing more slowly. On the it's stretched out, right? It's wider. It's growing. It's compressed vertically, but it's stretched horizontally. It takes. I have to go all the way to 4 to get to 1. Right? If I looked at the blue graph, I only had to go to 1 to get to 1. What if the value of a is negative? Right? So notice what happens. Again, our vertex still is at 0, 0, because we didn't translate. But if we take a point on, here we'll go on the left side here. So here we have the point on the blue graph, negative 1, 1. Oh, that looks terrible. Let's make that a little bit easier to read. Negative 1, 1. If we look at the red graph, when x is negative 1, y is now negative 1. It's the opposite. So notice any x on the new red graph has a y value that is the negative of the original blue graph's y value. So the graph negative f of x is a reflection about the x-axis of the graph of f of x. The new graph is obtained by flipping or reflecting the function over the x-axis.